Okay. Hello. My name is Rafiqul Gani, and together with the Thai team in Bangkok, we are going to give this workshop on decarbonization by simultaneous heat integration and optimization. There will be theory and application in terms of case study problem solution. The workshop is divided into two parts. The first part will be given by me on the theory and concepts and method. And in the second part, the Thai team, Ora and Jakrapat, will show how problems can be solved with the latest computer-aided methods and tools. So welcome to this workshop. I think you are all from Thailand. Unfortunately, I cannot speak in Thai. So speak slowly. If you have any questions, please show your hand. Then one of the team members will unmute you so you can ask your question. Or you can send your question to chat and they will read it out for me. It's not a problem to ask the questions while I'm speaking. More questions would be all right. So let me start now. Let me see if it forward. Okay, so decarbonization is a very important word these days, but it means a lot of things to a lot of different people. So we will try to define what we mean and what are the effects of decarbonization, objectives of decarbonization that we will try to satisfy. So the goal for decarbonization can be measured in terms of CO2 released versus resources used. These are exact measurements, temperature increase, and things like that. Also, indirectly, one can measure the effects of decarbonization through effect on climate, availability of resources, uses and needs of products, and many more like this. Or also, which I think everybody should include, the decarbonization objective should be related to the 17 Sustainable Development Goals proposed by the United Nations. And there could be many more measures of the decarbonization objectives. So how can we achieve those objectives? The first one, obvious, is reduce CO2 emission by reducing energy demand. And there could be other ways. Utilize captured CO2, generate only the amount of CO2 that can be captured and utilized. Look for integrated solutions, taking into account regional constraints. Integrated solutions meaning power, water, process, everything together. And there can be many other ways to achieve decarbonization. And what are the means to achieve them? One of the things that we will show in this workshop is the integration of ideas, concepts to develop significantly better technologies, use new conversion and separation technologies, develop and use methods and tools that give significantly better solutions, and again, many more. We already know from the IPCC special report that between now and 2050, there will be 754 gigatons of CO2 released. Out of this, as you can see from the chart, 32% needs to be captured if we want to keep the CO2 level at the level that we want. So out of the 754 gigatons of CO2 that is captured, 32 needs to be reduced, 32% needs to be reduced by industry. So industry do have a responsibility to reduce the CO2 emissions. And so as you see in the green box here, this is the objective of the course. We want to achieve or focus on decarbonization by reducing CO2 emission, and reduce CO2 emission by reducing the energy demand. So the workshop has, and my lecture also has 3 parts: heat integration plus optimization, hybrid distillation schemes, process intensification. The objective of all of these is to reduce the energy demand and therefore reduce the CO2 emission. And we will see why we have chosen those, because they have also a reason for it. So the first part is heat integration and process optimization. So we look at first the process. It's a very simple diagram of a process. And what we want to do is to design this process, simulate this process so we can verify the design. We do analysis of the process, and then we identify points that are hotspots. And based on hotspots, we define targets for improvement. Targets for improvement are reduction of energy demand, which means reduction of the carbon footprint. So once we have identified the targets for improvement, one way to improve the process is through optimization. We find out which are the variables that cause the hotspots, and we optimize to maximize, minimize cost in the carbon footprint. So that's one way. Also, we can see, although in the process it's not shown, that there are streams that need to be heated, there are streams that need to be cooled. So that means we need to add more energy for those that need to be heated, and we need to remove energy for those that need to be cooled. That is called heat integration. And there are ways to do the heat integration. For example, the pinch analysis. I will go through this in more detail later, but can do pinch analysis, but this is a graphical technique. If we want to optimize, we cannot use the graphical technique because we need a mathematical formulation of the problem. So one thing we can see is that on the right-hand side, we do the optimization. On the left-hand side, we do the heat integration. So which one should we do first? The heat integration and then optimization, or optimization and then heat integration? Can we do it simultaneously? That we will do both the optimization and the heat integration. To do this, we need to convert the pinch analysis to a mathematical formulation that you see as the transshipment model. I will show afterwards how to derive this mathematical formulation. But if we can have this mathematical formulation, we can add it to the optimization problem, and then we can solve all of it together. So that is what is understood as simultaneous heat integration and optimization. Why is this better? Because it has been shown that if we solve optimization and then heat integration, or heat integration and then optimization, the minimum that we will get from the simultaneous way would be much better. So what we want is the best solution, which is if we do it simultaneously. Okay, so with this background, I will now first introduce the concept of process design, simulation, and optimization separately. So what we do in process simulation optimization is what you see in the figure is a simple process flow sheet. All chemical processes have mixer, reactor, separator, divider. So it's a typical chemical process. What we want to do is to design the reactor, design the separator, choose the conditions of operation so that, as we said, the energy demand needed to run this process would be minimum, and also all the streams that are going out will not affect the environment. So if we have a design of this process, to simulate, we need a process. So what you see in here is the process model. The process model includes the model for the mixer, reactor, separator, divider, everything together. And that is represented in steady state by a set of algebraic equations. But to solve this algebraic equation, we need to first define the problem in terms of what is coming in, and we want to give all the parameters, which are the design parameters, and we want to calculate what is going out, what are the energy demands, and all of these things. So we define the problem, we retrieve the process model, and then, because there are many other variables in the process model, like the chemical data, the catalyst data, all of these things, we have to collect all the data. Once we have defined the problem, retrieved the model, collected all the data, then we are ready to solve. And after we have solved it, we then analyze the results to see if there are any hotspots and if the process needs to be improved. So that's the, in very simple way, the design and the simulation. Here is a more practical example of the process. This is a process to make cumene from propane and propylene. Propylene is the feed, propane is the inert compound. Propylene reacts with benzene to give cumene. And so we have the reactor, we have the separators, and there are two reactors, and then there are separators. So process design involves first to synthesize the flow sheet, and then on the flow sheet synthesized, we need to find the design conditions of the reactor, temperature, pressure of operation, the design of the distillation column, the design of the heat exchangers, if we need to change the pressure, either through a valve or expansion, all of these things we need to take care of before we can do the simulation. So again, we give what is the input, we give all the parameters of the equipment, which are the design variables, we then simulate, and we know all the variables in all the streams and also going out. And then we know the reboiler duties, condenser duties, and all these. And all those condenser duties require energy that is given by the process, let's say a power plant, and wherever there is a compressor, the electricity is needed, that is also giving, releasing CO2. So we have this process, we analyze this process, we find out what is the cost. So this is what we would call a base case, because whenever we are doing decarbonization, similar things like this, we always need a reference. And so this is the reference. Whatever we do, the alternatives has to be better than this reference. So we check, for example, the energy demands in all these unit operations in this flow sheet. And then we list all the energy demands, and then we find out that this distillation column, the reboiler duty and the condenser duty are the highest. Then our we will improve this process by reducing these two. And by reducing these two, automatically we will reduce the energy demand, which means we will use the carbon footprint, means that we will make more profit because we will pay less for the energy. So we formulate the problem, we solve the problem. But now we need an optimizer because now we have an objective function and we need to solve the optimization problem. So we go back to our definition and then we see that everything here is all right. But in here, in the solution of the problem, we see that in addition to the solver, equation solver, we need an optimization method. And in this case, it's a nonlinear programming method because there is no integer variables. And if there is an optimization method, it also needs additional equations, which is the objective function and the constraints. So now we have the process simulation and the optimization together to solve the problem. But still, remember, no heat integration. So now we can solve this problem. And once we solve this problem, we find out that the energy demand here has decreased and the profit has increased. So we have improved the process. But can we improve further? What we see is that there are heat exchangers that need to be heated, and there are heat exchangers where we need to cool. So some places, the temperature needs to be cooled, for example, from 342 to 240. In another place, we need to cool from 342 to 240. So we have heat exchangers that need cooling, and we have heat exchangers that need heating. By combining the heating and cooling, can we save energy? That's heat integration. So now we can solve this problem separately by doing the pinch analysis, as I showed, indicated to you in the concept slide, but we will look at it in more detail. So we have looked at this part, but now we will look at the heat integration part, the methods for pinch analysis and the mathematical formulation of the problem. So let us assume that we have two streams. They're called hot. They have to be cooled from this temperature to this temperature. And we have two cold streams. They need to be heated from this temperature to this temperature. And the Q is equal to FCP delta T that can be calculated. So to cool from this temperature to this temperature, so much heat has to be removed. And so much heat has to be removed here. So much heat has to be added. So much heat has to be added. So first law of thermodynamics is the conservation of energy. Whatever energy comes in, goes out, plus addition or removal has to be equal. And the energy Q is calculated from F is the flow rate, Cp is the specific heat, the product of this multiplied by the temperature difference. And with that, we can calculate all four. And then once we have calculated all four, we can find out that in this system, 10 BTU or units of energy has to be removed. And note that all of this data that you see here comes from the simulation. If we have done the simulation, these are already available to us. So then the question is, if we have to integrate the hot streams with the cold streams, and if we can do that, then instead of giving all this energy, adding all of this energy and removing all of this, we only have to add this amount. So heat integration can save a lot of energy. And then we can make a scheme like this, that from the hot H1, we will give all the energy that it has to be removed to the cold stream C3. And from H2, we will give everything to C4. But C3 also needs more, so we have to give remaining from H2. And getting this and this is not enough. It needs 180. From here, it will be 170. So we give the 10 extra. So on paper, it looks fine. The question is it feasible? In order to check for feasibility, we have to go back to thermodynamics again and look at the second law of thermodynamics. And the second law says heat cannot be transferred from a lower temperature to a higher temperature. So if anything happened here, where from the lower temperature, heat was transferred to the higher temperature, then it is not feasible. So let's look at whether that happened or not. So now we go to the pinch analysis, the graphical one. We first write the temperatures of the hot streams only. So these are all the temperatures of the hot stream. H1 goes from 120 to 250. H2 goes from 100 to 200. And then we calculate for any period from 100 to 200 or 120 or 120 to 140, all the energy that is here is calculated. And then the cumulative is, this is 0, 0 plus this plus this plus this. So that is the cumulative. So we can have the whole cumulative enthalpy values corresponding to the hot streams. And then we can make a plot of hot composite curve. On the y-axis is the temperature. On the x-axis is the cumulative enthalpy. And then if we plot these values against these values, we get this curve. But that's not, we also do the same, need to do the same for the cold streams. And so we do the same thing for the cold streams. We have the cumulative enthalpy, we have the temperature, we plot, and we get this. Then the next thing is we have to combine the cold and the hot. And we combine the cold and the hot. And the nearest distance in the hot and the cold, the distance is here. And this is called the pinch point. And it's defined by the temperature approach that at this point, the difference between the hot and the cold is 10 degrees. But know that after the hot stream, there is one part here that needs heating. And after the cold stream, there is one part here that needs cooling. So what we saw before is not feasible. This is the feasible solution. We need at least this amount of energy to be added, this amount of energy to be removed, and everything else can be integrated. So we save energy, but there's something that needs to be added, there's something that needs to be removed. So that is the pinch technology. As I said, if we want to do the heat integration and optimization, and we want to use this method, we have to do it separately. After we know all the temperatures and duties in the process flow sheet, we can apply this method, draw the graph, and find out how much are needed. But we want to solve it mathematically. So let's look at how to do it mathematically. And so here we are taking a similar problem. Hot stream, we have streams, we have steam at 500 degrees C, cooling water between 20 and 30. And the approach temperature is 20 degrees. And we want to find the minimum utility cost. Utility cost is the cost of the heating and the cost of the cooling. So this is our original problem. We convert this problem into what we call an interval table corresponding to 20 degrees. So in order to do the interval table, we take the temperatures of the hot streams and we take the temperatures of the cold streams, and we have 4 intervals. And between the intervals, we can see hot stream goes from interval 2 to H1, H2 goes from 3 to 4, and similarly C1 goes from 3 to 1, and C2 from 4 to middle of 3. So once this, we need to calculate the energies within all these intervals. So the next step is from this interval table, convert it into this form. So now what we see is that with respect to H1, the total energy that needs to be removed is 280, and this is distributed to 60 to interval 2, 160 to interval 3, and 60 to interval 4. So the total energy that H1 needed to remove is distributed to these 3. Similarly, H2 energy is distributed to interval 3 and 4, and similarly C1 and C2. With this information, we convert this information into what is known as a heat diagram. So the interval boxes, and on the left-hand side is the heat source, H1 and H2. Total amount of heat H1 has is this. Total amount of heat H2 has this. H1 heat is distributed to interval 2, 60, interval 3, 160, interval 4, 60. And similarly this one, and similarly this is the heat sink. From here, interval, it goes to C1. C1 gets heat from interval 1, 2, and 3. C2 gets heat from intervals 3 and 4. So from this diagram, and now is the nice part. How do we get the equations? It's very simple. For every interval, like I'm showing for interval 2, around the interval, whatever is coming in and going out, we have to do the energy balance. So what we see here is R1 is coming in, R2 is going out, 60 is coming in, 90 is going out. So we can make the equation for this, and similarly we can write the equation for this, this, and this. What will the equations look like? So here is for interval 60 was coming in, 90 is going out, R1 is coming in, R2 is going out. So R1 plus 60 is equal to R2 plus 90, or R2 minus R1 is minus 30. That's our one equation. So similarly for interval 1, 2, and 3, we will get 3 more equations. And these are the equations. For the first one, so we have the 4 equations. And now with the 4 equations, you see the variables R1, R2, R3. What are those? R1 is, we can go back one more, sorry. Any energy that comes from interval 1 to interval 2 is R1. Energy coming from interval 2 to interval 3 is R2. Energy coming from interval 3 to 4 is R3. And then any steam that is added is here. Any cooling water is removed, added is here. So QS is this, QW is this, R2 are energy that are given from the interval above to the interval below. If any of the R1, R2, R3 are, that indicates the pinch point location. So now it is a simple linear optimization problem. We want to minimize this. and we want to find the values of R1, R2, R3. Not all cannot be negative, they can be 0 or positive. And any linear program solver will solve it very easily, showing that the pinch point is at R2. The point is here. And the minimum amount of energy needed is 60, and the minimum amount of cooling water needed to remove energy is this one. So that is the minimum utility cost. But we say it costs, but there is no cost item. If we want an item, then we need to reform this problem slightly so that we can also put different sources of energy and water. So we will look at the slightly modified, again, hot streams and 2 cold streams. We have a high pressure steam and a low pressure steam. They have different cost, and we have cooling water, which has different cost. And the temperature approach is given as 10 degrees. So if we do the interval table, I will not go through all this as before, but from the interval table, we will write the mathematical form of the equations for the optimization. And so we have now an objective function that will be minimized with respect to cost and with respect to the reboiler duties. And then we have the linear equations, and we have all this. So solution of this problem says this will be the cost per year to operate the heat exchangers, the amount of high pressure steam needed, amount of low pressure steam needed, cooling water needed, and where is the location of the pinch point. And it shows that there are 2 pinch points here, which means that between 400 and 390, there will be 1 pinch point, and 370 and 360, 1 pinch point. So the process can be divided into 2 parts. So now we see that we can obtain, if we know what are the hot streams, what are the cold streams, and what we want to achieve, and what energy sources we have, we can formulate the problem mathematically. So now back that, yes, if we wanted to add in, we don't need to do this, we can do this, and we can add these equations to the optimizer and let the optimizer solve for the process as well as the heat integration. Now, all of this is fine, but how do you get these equations? Do you manually do it, or do you want the computer to do it? So that's when a user module is needed, because the process simulators do not have this. So we have developed this ourselves. Therefore, if we know the hot streams and the cold streams in the process, and the user tells this is what they want to do, the program will automatically generate this and connect it to the optimizer in the process simulator. So from the user point of view, you will not to do very much except for defining the problem. Okay. So with respect to software tools, what will happen? So here is the protor, and here is the optimizer. Here is the heat integration module that we have developed. So the simulator is connecting the heat integration module and the optimizer. And so what happens is that during the simulation, when it needs to go and do the optimization, it comes here, and then it finds out that to calculate the objective function, it needs to first solve the heat integration module. From the heat integration module, it will get the reboiler duties, condenser duties, all of those things. It will go to the optimizer. The optimizer will give new values, and then it will continue. And this is what you will see in the case study applications. So that's, in very short, the heat integration plus optimization. I did not go into too much details of the optimization method or of the heat integration methods, but I think I gave you the basic concepts and how the method works. You need to learn more. There is a list of references and books, and you will find all of those information there. And I will move on now to the hybrid distillation schemes. Talking about, again, energy demand, and we are talking about hybrid distillation. Why is hybrid distillation? Because we can see from this figure, among the different separation techniques like drying, evaporation, distillation, extraction, adsorption, crystallization, among all of these, distillation is the most energy intensive. So if we want to reduce the carbon footprint or CO2 emission, the one to target is the distillation, because that is the one that uses the most energy. There's no point in trying to reduce energy here or here. Compared to distillation, they are insignificant. So we have to use distillation. And then we know that this data is quite old. Around 2005, there were 40,000 distillation columns working. But an updated number tells us that these days there are more than 150,000 distillation columns working. And they need a lot of energy. And therefore, if we target those, we can save a lot of energy and therefore reduce the CO2. So how can we do that? And at the same time, we cannot get rid of distillation columns because there is no alternative better than distillation. So that's why we call it hybrid, because we want to combine two different operations together to achieve the same objectives. And here are some values that you can see. What kind of distillation columns use the most energy? So it's the petroleum industry, petrochemicals, all those hydrocarbon columns are the ones that use the most energy. The ones that you see here are difficult separations, but they do not involve too much energy. The ones that use a lot of energy are the hydrocarbon systems. So demethanizer, deethanizer, depropanizer, the olefins separation before and after of naphtha, all of those distillation columns require the most energy. If we want to also target to reduce energy, these are the ones that we need to target. And what we have seen, and that is why we say that distillation is not the best. Up to this point, which is not very high purity, distillation is actually best. With very little energy, it can reach a reasonably high purity. But if we want to go from this point to this point, then what this curve shows is the reboiler duty versus the composition of the distillate. So as we go higher in purity, we need more and more energy. So if we see that this is 1 point, and from this point to this point, nearly 80% of the total energy is used to go from here to here. And on the right-hand side, the reboiler duty is converted to carbon footprint. So if we reduce the reboiler duty, we reduce the carbon footprint. So then the question is, if distillation is not good in this area, why should we use distillation? Can we stop with distillation here and add something that is more efficient from an energy point of view to do this part of the separation? So that is called hybrid distillation. By analysis, we have found out that one feed, simple columns like one feed and two products purity defined by the light key and heavy key, they always show this behavior. So here are alkane separations, alkane separations, alcohol separations, alkene separations. They all show the same thing. That the high purity section, most of the energy is used. So we can say this is the curve distillation, and we see that it requires a lot of energy to do the high purification. On the other hand, if we draw membrane curves, this is a membrane curve, this is a membrane separation curve, they do not use that much energy in this section. So can we do distillation up to up to here, let's say? And then from here, can we switch to membrane so that we avoid using all this energy here? If we can do that, then the scheme would be like this. Here is the distillation. At this point, we take the distillate, we send it to the membrane, and then the design of the membrane has to be special, because normally with the membrane, the permeate is the light compound and the retentate is the heavy compound. But we want to reverse the membrane so that the permeate is the heavy compound and the raffinate is the light compound. And then this will work, because if we have 90% of the light compound and 10% of the heavy compound, the more heavy compound we take out, the more pure the light compound becomes. And since membranes work only efficiently if the flux is low, if we are only trying to remove 10% of the heavy compound, the flux is low, so the membrane operation is also good. We are interested in, if we can find the membrane that will take the heavy compound out, and more heavy compound goes out, the light compound becomes more pure, and this heavy compound then is combined with this heavy compound, and we get the heavy compound. For this scheme, we do not need to change anything in the distillation column except the reboiler duty or the reflux. And by changing that, we change the product purity, and then we add the membrane. So how can we then are sure that the energy would be reduced, but how can we pay for it? So let's see. We say that our cutoff point for the distillation will be here, and the purity that we wanted was here. So this difference is the potential saving. If this saving is large, then we can calculate and find out from this saving an extra profit, how long will it take for us to pay back this. And usually if we can find a good membrane to take the heavy compound out, it can be between 3 months to 6 months. So we can actually, from the extra profit, we can pay for this extra membrane. So here is a typical distillation sequence that you will find in many petrochemical complexes, petroleum refineries. So we have a mixture of 5 compounds, but it can be more. And we start with, so it's after the demethanizer and deethanizer. propane, then butane, isobutane, normal butane, isopentane, normal pentane. So these are compounds. So we first remove propane, and then from this column, the two butanes are taken up, the two pentanes are going down, and then we have a separation of the pentanes, butanes, and the pentanes. So we design the process, we simulate this process, and then we find out where is the hotspot. That analysis is very important. The hotspot happens to be this one and this one. So these use more than column C1 and C2. So if we want to reduce energy, we have to target these two. So this is the blue curve is for column C4 separation. Just to be sure, this is column 3, this is column 4. C4 separation is column 3, C5 separation is column 4. So this C4, this is for C5. And then here is the cut point, and here is the actual if we only use distillation. Here is the cut point, and here is the actual if we only use distillation. So we want to save this difference in in C3 and this difference in C4. So we have identified the target. Now we can calculate, and we find out potentially for column C3, that is separating the C4s, we can potentially save 44%. And for the C5 separation, we can save 39.5%. So there is hope for improvement. Then there is a good idea to find out whether a membrane can be found to do the separation that we need. That could be found, and the membrane will take out the N-butane here and the N-pentane here, so that we get the pure isopentane and pure isobutane. And it turns out that if we then take the profit and use the profit back, we pay back this one within 3 months, we pay back this one within 6 months. So not only we make a profit, we also improve the environment and reduce the carbon footprint. So it is possible to improve the environment and at the same time make profit if the problem is formulated correctly. And what we need here is no change in the distillation column. The only change we make are add 2 small membrane units. And we reduce the reflux in this column and in this column, and nothing else is changed. And the columns work perfectly at this lower reflux. And because the reflux is reduced, the purity is reduced, and the reboiler duty is reduced. Does it work for other systems? Here are other systems. Separation of this we already know. This we already know. Methanol water, 2,2-dimethyl butane, hexane separation, styrene ethyl benzene, benzene cyclohexane, acetonitrile water. So all of these are taken from the literature of existing columns, and we have shown that so much energy can be saved. Other hybrid schemes, we can put the membrane before the distillation column. Sometimes it works. The one I've shown you is after the distillation column. We can put the reactive distillation, the membrane, everything inside. We can have the reactive distillation membrane, and then further purification in the distillation column. We can also add membranes in a dividing wall column. So all kinds of combinations are possible. The main thing is that if we add a membrane, we need to remove the compound in the smaller amount, because the membranes will work efficiently only when the flux is low. So wherever we put, we want to take the compound in the smallest amount. And therefore, if we put here, the compound in the smallest amount is the heavy compound. So we take that out and the light compound becomes purer. So that's the idea. Here, the idea of the membrane is to remove a compound that forms isotope. By removing the compound, we get rid of the isotope or go to the correct side of the isotope. And that is the case here also. So all kinds of combinations are possible, and they will all save energy and therefore reduce the carbon emission. Here, or theory here, is the dividing column. So what is the dividing wall column and when do we use it? Dividing wall column needs to be used whenever we have more than 2 distillation columns, at least 2. More than 1, that is at least 2. So if we have 2 distillation columns, we are separating 3 compounds, showing the case for 2 distillation columns. So we are talking about simple columns, 1, 2 products, and A, B, C separated in this way or in this way. So instead of using 2 distillation columns, dividing wall column says that you can put one of the columns inside and have a division here, and the other column is the main column. And then we can get A, B, C. Here is A, here is B, here is C. So dividing wall columns can be used for ternary separations. And if you have quaternary, then you need more columns. But for ternary separations, instead of using 2 columns, 1 column could be used, but another column is inside. Now, in order to design and simulate this process, one has to do 3D modeling to do this kind of simulation, but the standard process simulation in 1 dimension, these are done like this. So this column is here, and the other section is here. And then the vapor from this goes to here, and the liquid goes from here goes to there, and the vapor from here goes to here, that is here, and the vapor liquid from here goes to here. So here is the liquid going, here is the vapor going, here is the liquid going to the column, and here is the vapor going. So from a simulation point of view, this is how the process is simulated. But the actual process looks like this. So now, let us say that we want to separate a mixture, again, taking from the petroleum industry, and this is starting from the de-ethanizer. There is more ethane than anything else. So ethane, propane, isobutane, N-butane, and the C5s are put together. And we want all products. How many ways can we get these products by just separation? We can do what is known as a superstructure. We have the feed here, and we have the 5 products here, and there are different ways. We can go this way, this way, this way, this way, this way. So that would be one. We need, if we have 5 products, then we need minimum 4 separation steps. So which separation to use here, separation to use here, which one to use here, which one to use here. All these combinations give us a large number of schemes, 184. And out of that, we found out that this separation with simple distillation columns is the optimal. So these are all with distillation columns. So if this is the optimal, now we will try to make this as our base case reference, and we will try to improve further. So this is our base case. And now we will try to do is combine two distillation columns to become a dividing wall column. We can say that these two we can combine, or we can combine these two, or we can combine these two. So there are three ways we can make dividing wall columns, three different pairs. Which one is the best? So we looked at all combinations, and it turns out if we combine these two together, and then with the ethane purity, if we reduce the reboiler duty on this column and put a membrane, we save energy 45% compared to the original. So it's a big saving possible. So the only difference is that the dividing wall column, what is the cost of the dividing wall column compared to the cost of these two? But the saving is quite large. From an operational point of view, the dividing wall column has two issues. Let me first show you the two issues. Is that the liquid that is coming to this column from the main column to the prefractionator, and that's the liquid, and the vapor that goes in here. These two, they have a minimum flow rate. If the flow rate is lower than the minimum, there will be no liquid or no vapor here, and then there will be operational problems. So the simulation and the design and the starting up is a little bit difficult, because one has to be sure that one is starting from a stable condition, meaning that these flow rates are higher than the minimum. And it can take a little bit time in actual operation for it to come to steady state. But once it is at steady state, this configuration will give 45% less. So what are the different ways to combine? As I said, if you have three compounds, A, B, C, and you want pure A and C, B cannot be very pure, but A and C can be very pure. That separation, dividing wall column, is good. If you have four compounds, then you can remove A first and have B, C, D, and B and D can be very pure, but not C. Or you can remove D first and then separate A, B, C, which is like this, and A and C will be pure, but not B. The product that comes out at the middle is usually not very pure. But one can put a membrane and other things to make it more pure. So very short, this was what could be done with dividing wall columns, and you will also see examples. Is there any questions? Okay. Okay, so to summarize, we can take a base process, and we see that in the base process, the distillation is energy expensive, energy intensive. The long-term solution could be that we totally replace distillation. But at this moment, there is no technology that can totally replace distillation. Membranes can do, adsorption can do, but only for small flow rates, not big flow rates. And these are large flow rates. So the long-term solution, we still need to wait for technology to be totally replacing distillation. But short-term solution, as I've shown you, is another figure here. We can just add a membrane unit and keep the original distillation column as it is, and we will save significant amount of energy. The rule combine two types of techniques, distillation and membrane, that operate at their highest efficiency. Distillation only up to the purity at which it operates very efficiently, and membrane only for small flow rates. Savings of 10 to 50% can be achieved, and this is the correct figure now. There are about 200,000 distillation columns operating on Earth. If we can save between 10 to 50%, we will make a big impact. The question is the industry ready to do that? The technology is there as the short-term solution. It's the industry that needs to take advantage of this. Okay, with this, I go to the final part, is process intensification. So, and there are many ways to do process intensification. The one I'm going to highlight is reactive distillation. So if you look at these two processes, here is a reactor, here is a reactor, followed by separations. And the reaction is exothermic. And the separations are all vapor liquid. So if we have situations like this, exothermic reaction, vapor liquid separations, it is possible to convert these flow sheets into one unit operation with reactive zone here, stages, non-reactive stages, condenser, reboiler. So the question of the design is, what should be the number of stages here, number of stages here, number of stages here? What should be the duty of the condenser, reboiler? So this unit operation can represent this or this. And this is also a short-term option. There are many, many processes. These are two industrial processes that can be, at this moment, converted to a reactive distillation with significant improvement in energy. How does this work? I will give you an example with methyl acetate problem, which is this process flow sheet. And afterwards also, the Thai team will show you examples. So first, we define the problem. We have the reaction, acetic acid plus methanol giving methyl acetate water. And we want methyl acetate purity of 92% or higher. We have the objective function to minimize the cost or maximize the profit. Here is our base case flow sheet. This is an actual flow sheet that existed at Eastman Chemicals. And we first take the design, simulate the design, and find out where the hot spots are. The hot spots are here. It requires a lot of energy. And another one here, we are losing a lot of the reactant. So both needs to be stopped. We need to stop the reactant. We need to reduce the energy cost, but also material cost. How many distillation columns are needed? Can we reduce them also? So that's the target. So we need to reduce the utility cost, energy cost. These are very high. There is loss of energy in the system. The carbon footprint is high because the energy demand is high. So, and then we find out from the flow sheet. Let's go back to the flow sheet then. This is column 1, column 2, column 3, column 4, 5, 6, like that. So column 2 is very high, column 1 is very high, the other ones are high, but columns 2 and 1 are very high. So if we want to do anything, we have to reduce these. So we look at the utility cost, we see here. And if we look at the carbon footprint, the highest in terms of utility, this is the highest in terms of carbon footprint. This is the higher. After this one, this is also. So then it's clear T1, T1 and T3 should be targeted, and we need to reduce them. So we want to reduce the energy demand. We want to reduce the number of unit operation. We do not want to lose acetic acid. So we want to increase the conversion. We can explore hybrid operations. We want to improve sustainability, LCA factors, and you can say contribute to circular economy. All of these related to decarbonization. So first we do a process analysis, and the process analysis that we have methanol, acetic acid, water, and methyl acetate. Methyl acetate is the product. So from these four combinations, four chemicals, we have 6 combinations of compounds. Methanol, acetic acid, methanol, methyl acetate, methanol water, acetic acid, methyl acetate, acetic acid water, methyl acetate water. So if we want to do any separations, any of these combinations can cause problems. What we see is that methanol water, of course, is no problem. It's easy to separate. However, the combination of methyl acetate water, methyl acetate methanol, acetic acid water, they form azeotrope. And if they form azeotrope, then getting pure products by distillation is not possible. That's why they had to use many columns and also solvents. What we see is that these azotropes, this is this one, this is this one, this is this one. If we change the pressure, the azeotrope composition changes. So we can take advantage of changing the pressure to get the separation we want. So thermodynamic insights and pure compounds values tell us something about the separation problems. That separation of methanol water is easy. We have to worry about separating azotropes, but if we can play with the pressure, separating the azotropes could be easier. So then the tasks we have is we have a reaction task, that is acetic acid methanol reacting. Then we have a separation task. We want to separate acetic acid methanol. We want to separate methyl acetate methanol. We want to separate methanol solvent if you add a solvent. So all this, and there are many more separation tasks we have if we look at the original. But we want to reduce the separation tasks also. So we said that we have a reaction task, and then after that, since we have 4 compounds, we have only 3 separation tasks. And then this is one separation task, and we have so many alternative ways to do it, and the second one and the third one. And we take one of these as an example. So here is one example. Acetic acid methanol comes to the reactor. Then we have a separation task where we take the water out. Then we have a separation task where we take the acetic acid out. So water and acetic acid the acetic acid comes back. Then we separate methanol. Methanol comes back. And then we separate the product, methyl acetate. So one of the product, water, is taken out here. Another product, methyl acetate, is taken out here. So this is a simple flow sheet, much simpler than the one before. Can we improve this? We can by putting a membrane separator here. So this is a membrane separator. This is a reactor, followed by a membrane separator, followed by these three. Then can we combine these two together? So now we combine these two together, we combine these two, and these are three. And then these three together, we can make it in a reactive distillation by putting this one below and these two above. And the methanol is recycled back to the column, and the acetic acid is recycled back. So we have the methyl acetate product and the water product. So just by simple analysis, we can see that starting with a complex flow sheet, we make it a simpler flow sheet, and we get the reactive distillation. Another way, more theoretical way we can look at it also is possible. And this is called studying the thermodynamic insights and phenomena. To separate methyl acetate and water, we can use membranes, and the membrane will take out the water and we get the methyl acetate. So can we identify all the phenomena that we need in this process? And what are the phenomena? This is R is reaction, M is mixing in liquid, mixing, fluid mixing, mixing of vapor, two-phase mixing, phase contact, vapor liquid, phase transfer, vapor liquid, drying, heating, cooling. So there are about 15 phenomena. Can we combine them together to make different operations? If we combine them, we get about 16,000 combinations. That will give us operations like this. But heating and cooling cannot happen at the same time. Drying and cooling cannot happen. So if we take out some combinations that are not possible, we get only a reduced number. So we have only 64 combinations that work. What are those combinations? So here is a separation task. We do mixing, two-phase mixing, phase contact between vapor liquid, phase transfer between vapor liquid. What kind of separation is it? For example, a flash. If we also put the reactor, R is reaction, then we have a two-phase reactor. So by combining these things, we can make the different tasks. And so we can say, okay, we can make these different tasks. Let's mix liquid and do the reaction in liquid. That becomes the liquid phase reactor. Let's make a mixing of the liquid and cooling. That's a mixer. Similarly, we have a separator, another kind of separator, like a membrane separator, and we add reaction to have a reaction separation. We can also combine these two together. Then we have a liquid phase reactor, which is cooled. By combining these together, we have a distillation column. We have a distillation column, and we keep this like it is now. So we can see that from the phenomena, we can get what we call SPB, which are basic structures, and then, basic phenomena. And then by combining the SPBs, we get the basic structures, which look like unit operations that we know. So now we go back to our reaction task, which is this and this going in, and these compounds going out. And then the separation task, 4 compounds. And if we remove water, we have 3 compounds left. And then if we combine these two together, we have these two coming in, and then we have these going out here, this going out here. So reaction separation we have combined. Now this separation is here, we do the first separation, take out the acetic acid, and then for this separation, we take out, do the separation at a different pressure so that we can get the pure methyl acetate, and methanol we recycle back. So if we combine these two together, and note that these are reactants that will be recycled back, we get the reactive distillation. So now you have seen in different ways we can take the process flow sheet and we can get a design of the reactive distillation. Let's just skip these things here. The only thing to mention more is this part here. This is the reactive distillation. In the central part is this. Then above the reactor stages is this. Below the reactor stages is this. This is the reboiler. This is the condenser. See here, C and H. And the nice thing about it is that we can have as many of the reactive stages and the non-reactive stages. By increasing this for more than one, we can keep on increasing until we get the product purity we want. And then we know how many stages are here, how many stages are here, how many stages are here, what is the condenser duty, what is the reboiler duty. And so that is the way to convert any process flow sheet to a reactive distillation. And what you will notice is that if you look at the encyclopedias, Kirk and Altmer, or the hydrocarbon processing annual yearbook, they have process flow sheets, hundreds of process flow sheets with reactor followed by separation, exothermic reaction, and separations are vapor liquid. All of them can be converted to this. So we have seen how the design is. Is it energy efficient? So now here you see this. Here is the base case. And here is the reactive distillation. So from 21, it's only 2.28. So significant reduction in energy is possible. You can see that the profit has increased, but not much, because the reactive distillation is costly at this moment. But except for the cost of the reactive distillation, everything is very promising. And if we look at it from a radar plot, the boundary is the base case, and all the alternatives, including the reactive distillation, are inside. So from a sustainability, circular economy point of view, we have identified alternatives that are better than what we have. And at the same time, we are making profit. We are reducing the carbon footprint. So now we come to the conclusions. Why are we doing this? Because on Earth, we need to convert our resources to the products. That's why we have the process. We take oil and we convert it into olefins and ethylene and propylene and benzene and polypropylene and all kinds of products. Whatever products we make, we also need energy. And if we need energy and if we use fossil fuel, then we are going to release CO2. We also need water, and fresh water also is a problem. Whatever we do here and here, we affect the environment and our health. And we also have to worry about our food resources. And they are all interconnected, and we need to face the challenge tackle this challenge and especially look at these, but not just this, we need to look at all of them. What I've shown is we can look at this one and this one, they will work together. If we reduce the energy, we also reduce the environment health aspects. And we can also reduce the food aspects. But the problem can be seen also from here. By 2050, the population on Earth will be between 10.5 to 11 billion. That will need a GDP increase. And with the GDP increase, we will need more production capacity for steel, chemicals, food, and other. That will require more energy, more electricity, more water, and all of these will need more, will release more greenhouse gas. So if we want to tackle this problem, we have to worry about this, and we have to make use of the technologies that reduce the energy demand. At least that part of decarbonization we can tackle very easily. One final thing I want to show is that all these things that I've shown, if one thinks of that, yes, if we have a simulator, the simulator will solve all these problems. It will not, because what you see here is what the simulator has. It can solve the problem. It has the thermal library, database, solver, model library, flow sheet. So it can solve many problems. But what happens if you do not have the flow sheet? The simulator does not generate the flow sheet. What happens if you do not have the model? What happens if the reactive distillation or hybrid membrane distillation model is not there? Or if you need solvents or catalyst is not there? The simulators don't solve these things. The user has to give them. So just if one has the simulator is not enough. It is necessary to have a large number of tools working with the simulator. And these are some of the tools that I will show you. So we need a library of databases, not just properties, but we need to know about the solvents, we need to know about the reactions, we need to know about the hazards of the chemicals, all of these. Then we need to be able to generate process flow sheets and calculate the carbon footprint, energy index, safety, environmental, all of those. We need to be able to size a new flow sheet, design intensification process flow sheets, as I showed you, design hybrid operations, as I showed you. All of those design methods we need. If we have all of these, we can then use a simulator to verify whether our designs are not. And then once we have the simulation, we can do also analysis in terms of circular economy, LCA, sustainability, and so on. So what we see again is that if one has the simulator, it only solves this problem. Not solve this problem. And so one needs all of these in order to get the solutions we need. And the solutions we need, the energy reduced technologies using intensified process, hybrid process, or combined heat integration and optimization. Just the simulator does not do it. So hopefully one gets this message. References, these references we have used. And finally, the next part will be done by the Thai team. And they will show examples of heat integration plus optimization, examples of distillation, hybrid distillation, and process intensification. Hybrid distillation will include dividing wall column as well. So they will show actual problem solution, not just examples, but actual problem solutions.